Hi friends, today we discuss about the geometrical isomerism. Geometrical isomerism having the here staggered conformation and eclipse conformation. Here cis-2-butene having the boiling point plus 4 degrees Celsius. Here trans-2-butene boiling point 1 degree Celsius. Cis means having both hydrogens are present on same side, and here trans means on opposite side. The particular type of diastereomer that shows their existence due to restricted rotation about the double bonds are called as a geometrical isomerism or geometrical isomers, and the phenomenon is called as a geometrical isomerism. There are different types and there are different conditions for geometrical isomerism. The first, the groups attached to each olefinic carbon atom must be different. That means the olefin having general molecular formula ABC, which is equal to CXY. Here A not equal to B and X not equal to Y. Olefin means carbon-carbon double bond. Here isobutene, one is hydrogen, other group is methyl, here propene, and one butene. In these molecules there is no geometrical isomerism. What is the important condition for geometrical isomerism? The groups attached to each olefinic carbon atom must be different. Here same atoms are present, so here no geometrical isomerism. See here geometrical isomerism. Cis isomers, that means Latin, what is the meaning of cis isomer? On the same side, on the side, that is cis. When similar groups are on the same side of the double bond, it is called as a cis isomer. And when trans isomers means Latin across, when similar groups are on the opposite side of the double bond, it is called as a trans isomer. This is the difference between cis isomer and trans isomer. Then geometrical isomerism, here type first, both hydrogens are present on the same side. Here in second type AA, B, D, and third type A, B, E and D. There are different atoms or molecules are connected to the carbon-carbon double bond. Then E and Z configuration. Here E isomers, when both first priority groups are on the opposite side of the double bond, the configuration is designated as a E isomer. German integer meaning the across. Here give the priority 1, 2, 1, 2. E isomers, when both first priority groups are on the opposite side of the double bond, the configuration is E isomer. Then see here what is meant by Z isomer. When both first priority groups are on the same side of the double bond, the configuration is called as a Z isomer. German zusammen meaning the together. Here both first priority groups are present on same side. But when you consider the E isomer, at that time when both first priority groups are present on opposite side, but in Z isomer first priority groups are present on the same side. That isomer is called as a Z isomer. Here there are different rules for assigning of priorities. Then that rule is called as a sequence rule. According to atomic number, the atoms with the highest atomic number is assigned first priority. Here different atoms are there. According to their atomic number, the priority is given. Hydrogen having the less atomic number, so the priority of that hydrogen is later. Okay, here molecule is there. Here in iodine and hydrogen, iodine having the highest atomic number, so first priority, hydrogen lowest priority, so second priority. In methyl and bromine, Br having the highest atomic number, so first priority, methyl having second priority. Here iodine CH2 Br, Br CH3, iodine having the first priority, methyl having the second priority. Here bromine having first priority, CH2 Br second priority. Then see here both having the E isomer. Why this molecule having the E isomer? Because the priority groups are present on opposite side. That means first priority groups are on opposite side. So this is the example of E isomer. Then second rule, if two atoms directly bounded to the olefinic carbon are isotopes of the same element, the atom of higher mass number has highest priority. Okay, here isotopes are there: hydrogen, deuterium, tritium. Hydrogen 1 atomic number, deuterium having 2 atomic number, tritium having 3 atomic number. So the third rule is, if two identical atoms are attached to the alkene carbon, then the priority is determined by comparing the atomic number of next set of atoms. Here CH3, C double bond C. That means what is here? If two identical atoms are attached to the alkene carbon, at that time we have to go, or we have to compare the atomic number of the next set of atoms. Here CH2, CH2. And to that CH2, one CH3 is attached and next Br is attached. So you have to take the priority first of Br, not the CH3. Then here hydrogen, hydrogen, carbon, hydrogen, hydrogen. Here first priority goes to CH3, CH2, then CH3. And in second one, first priority goes to CH2, Br, then CH3. So the first priority groups are present on the same side of the carbon-carbon olefinic bond. Say the isomer is Z1. Then rules for assigning the priorities. Here different examples are there. Here first priority, second priority, first priority, second priority. You have to compare the next atom. When you consider the right hand side of first molecule, at that time CH2 attached to OH and CH2 attached to Br. So the first priority goes to Br, then that of hydroxyl 1. Same on the same side here, CH2, CH2. So methyl groups are attached higher in first priority. So goes first priority. That means here the first priority groups are present on the opposite side of the carbon-carbon double bond, olefinic bond. So this isomer is E isomer. Here same example is here, gives the priority, and so both the first priority atoms are present on opposite side of olefinic bond, carbon double bond carbon atom. So this isomer is E isomer. And what is the condition for Z and E isomer? When the first priority groups are present on the same side, at that time this isomer is Z isomer. But when the first priority groups of the both first priority groups are present on carbon double bond carbon opposite side, at that time this isomer is E isomer. Then fourth rule is groups containing multiple bonds. If the groups directly bonded to the olefinic carbon atom double or triple bond, it is considered to be equivalent to 2 or 3 single bonds with the same atom respectively. That means if the groups directly bonded to olefinic carbon having the containing double or triple bond, at that time you have to equivalent to 2 or 3 single bonds with the same atom. See here the example. Here different examples are there. Carbon is directly attached to 2 oxygen. Here carbon is directly attached to, just 2 minutes. Carbon is directly attached to 2 oxygens, and here carbon is directly attached to 3 oxygens. So we have to take the priority oxygen, oxygen, hydrogen, and then carbon, carbon, carbon. Here giving the priorities order according to the carbon is directly attached to oxygen, and here carbon is directly attached to carbon. So priority goes to carbon double bond oxygen. The next rule for assigning the priorities, having the different examples here. Carbon goes to carbonyl group, then hydroxyl. Here carbon is directly attached to CN. So the priority goes to C double bond oxygen OH, then C triple bond N. The second example here, pH is there, here CH3 is there. That means carbon is joined to 2 carbon atoms. So priority goes to phenyl, that means benzene ring. Then priority goes to methyl group. Then assign E or Z. Here carbon having iodine and hydrogen, so priority goes to first iodine, then hydrogen. In the other side, priority goes to bromine, then priority goes to chlorine. Bromine having highest atomic number than that of Cl, and iodine having the highest atomic number than hydrogen. So both first priority groups are present on the same side of olefinic bond, so this configuration is Z configuration. Then second example here, CH3 and hydrogen. CH3 having highest atomic number than hydrogen, so priority goes to methyl, then hydrogen. Again we have to compare CH2 CH2, but CH2 attached to OH and CH2 attached to NH2, so the priority goes to CH2 OH because having the highest atomic number, and CH2 NH2 having the second priority. So here again both first priority groups are present on the same side of olefinic bond, so this is the Z configuration. Then see here next example, Br and Cl. Br having the highest atomic number, so priority is first and Cl is second priority. Again we have to compare the NH2 and OCH3. Oxygen having the highest atomic number, we have to consider first atom. Here nitrogen and oxygen is the first atom, so oxygen having the highest priority, so OCH3 is the first priority, NH2 is the second priority. Again here both first priority groups are present on the opposite side of carbon double bond carbon, that means olefinic bond, so this isomer is E isomer or E configuration. Then next example, CH2 CH3 and CH3, so priority goes to CH2 CH3 first and then CH3. Then in Na2 and NH2 the priority goes to Na2 then NH2, so both first priority groups are present on the same side of olefinic bond, so the configuration is Z configuration. Then next Cl and CH3, Cl having the highest atomic number, so the priority goes to Cl, then second is the CH3. Here pH and CHO, then CHO carbon is directly bonded to oxygen and here carbon is directly attached to carbon, so the priority goes to CHO then pH. In this molecule both first priority groups are present on opposite side, so here configuration is E. Then next example, Br having the highest atomic number, so priority is first. Hydrogen having lowest atomic number, so the priority is second. Again we have to compare the priority of COOH and C triple bond C. In COOH carbon is directly attached to double bond oxygen and OH. Here carbon is directly attached to carbon's triple bond carbon, that means priority goes to COOH first, then second having C triple bond CH. So in this molecule the both first priority groups are present on the same side of olefinic bond, so the configuration is Z configuration. Then physical properties of geometrical isomer. Geometrical isomers have different physical properties such as melting point, boiling point, refractive indices and solubilities density. Here cis-2-butene and trans-2-butene. Here boiling point 4 degrees Celsius, here boiling point 1 degree Celsius. Then this is more polar. Higher order of symmetry, it's perfect and strongly. Then geometrical isomers have different chemical properties. Here malic acid is there, and when heating takes place at 140 degrees Celsius, there is a formation of malic anhydride. Then this is the cyclization reaction of fumaric acid. When reaction takes place at 140, no reaction. This is the isomerization. There is a formation of malic anhydride. This is dihydroxylation reaction of malic acid in presence of KMnO4. There is a formation of mesotartaric acid, and when the reaction takes place of fumaric acid, trans-tube fumaric acid in presence of dilute KMnO4, there is a formation of DL pair of tartaric acid. This is the dihydroxylation reaction of malic acid and fumaric acid. This is the cis malic acid and trans fumaric acid. Thank you.